Welcome to the fluid part of the course for AP Physics 2. These are the formulas that I've labeled on my version of the formula sheet F1 through F6. I want to talk about them a little bit and then go through some example problem solving. We're going to talk about some aspects of fluids in class, but obviously this year we have to do some things out of class as well. I asked you to read sections 13.1 to 13.5 and gave you a couple extra pages of handout from chapter 12 that relate to fluids and pressure, especially with regards to gauge pressure and absolute pressure. So this first formula is in section 13.1. It's density. The Greek symbol here, rho, it looks like a P with a little swoopy thing. It's a lowercase Greek symbol rho. It's equal to mass over volume. That is density, mass per volume. The standard units for that in the metric system are kilograms per cubic meter. Just for reference, water at a normal temperature has a density per volume of 1,000 kilograms per cubic meter. Things that would sink in water would be more dense than that. Things that would float in water would be less dense than that. So big idea, objects that are more dense sink, objects that are less dense float if they're in a liquid. If it's solids or other things, it gets a little more complicated. This formula deals with pressure. It's the fundamental way to think about pressure. So pressure is force divided by area, newtons per square meter. So 1 Newton per 1 square meter is also known as a Pascal. That is the standard unit of pressure. Kilopascals are often what we think of with atmospheric pressure because the 1 atmosphere of pressure, which is about 15 pounds per square inch in English units, is about 100,000 pascals in terms of metric units. So fluids also experience pressure at depth based on all the molecules that are above them. So if I look at my hand here and I pick out a 1 square inch area, again, it has about 15 pounds of pressure on it. You might say, well, why is my hand forced down like that? Well, there's pressure on all sides at an equal depth. So at this point, the pressure is the same on the side, the bottom, the top, the sides of my hand. So there's not a net pressure or a net force in any one direction. That's true for liquids at a depth also. So the pressure at a given position, either gases or liquids or combinations, is a result of all the molecules that are above it. So the deeper you go, or the closer to the ground you go, the greater the air pressure is. So air pressure is less in the mountains, for example. And there are other climatic effects which can affect air pressure as well. If you're under a liquid, the total air pressure is actually a combination of the atmospheric air pressure plus the extra pressure caused by the liquid at a given depth. So that's this formula, F3. So this would be your absolute pressure. This P0 or P0 would be the atmospheric pressure. At sea level would be traditional, so about 100,000 pascals. Density of a liquid, G, 9.8 newtons per kilogram. And H, or depth, probably should be a D there, of the liquid below the surface. So at a given depth, the pressure is the same everywhere, even if the top of the liquid varies due to different shapes. So we'll talk about that a little bit in class and get some examples about that in class. And that's fantastic. So this would be essentially the absolute pressure, atmospheric pressure. This would be treated like a gauge pressure. It's the extra pressure in something, by the way. So gauge pressure is a difference in pressure. Examples, if you have a tire gauge, and let's say you put a tire gauge in a car's tire, and it might read, say, 29 psi, pounds per square inch. That's about 200,000 pascals or 200 kilopascals. What that really means is the pressure inside the tire is 29 pounds per square inch greater than outside. So the absolute pressure inside is around 29 plus 15. That's about 44 pounds per square inch. So gauge pressure is useful because it measures a difference between two cases. When we think about pressure at depth, we think about that not moving, and that's called hydrostatic pressure. So big idea, in an open container, the pressure at a given depth must be the same if the fluid is at rest. That's called Pascal's principle. And we're making some assumptions, like, for example, the fluid's incompressible. A barometer is basically a tool, as also mentioned on page 446. Traditional barometers have used mercury. Current ones use digital ways of measuring pressure because mercury is pretty toxic. Section 13.3 deals with buoyancy. That's the upward force of a liquid on a floating or submerged object. Big idea, the buoyant force is equal to the weight of the liquid displaced or the fluid displaced. Essentially, an object pushes the fluid aside, and therefore that's a Newton's third law interaction force. So if you think of an object that is underwater, you could say, let's say it's a lead weight or something like that. Lead weight pushes on water, water pushes back on lead weight. So really a buoyant force is a force of the liquid acting on the object, causing it to want to float. Want is a bad word for that. But that idea of the fact that the buoyant force is equal to the weight of a displaced fluid is called Archimedes' principle. So this acts on either floating objects or submerged objects, because the floating objects are at least partly under the liquid. And actually, that's interestingly enough true for us as well. So if you stand on a scale right now, the density of air is much lower than anything around us. And so your weight would, let's say it's 150 pounds. If you did that in a vacuum, where there's no air that your body is pushing aside, you would weigh slightly more. So actually your weight is probably a little higher than is read on a scale. Not much, because normally we end up having a fairly small volume in terms of cubic meters, and the density of air is pretty low. However, if you're underwater and standing on a scale, you notice the reading would be almost nothing, because the density of a human body is about the same as that of regular water, since we're made of mostly water. So the buoyant force, again, is equal to the density of the liquid multiplied by the volume of the liquid multiplied by g. All that equals the weight of the liquid. Why? Well, if we rearrange this equation, we see that mass is equal to density times volume. Density times volume times g is mg. mg is the weight of something. So really this is figuring out the weight of the water that's displaced by the object that's either submerged or partially submerged. So that's kind of important. Again, we'll go through some examples in class to help figure some of those things out. A thinker question I could ask you would be, would an object that floats in water float higher or lower compared in seawater compared to fresh water? So seawater is more dense than fresh water. So think about what that might be. Section 13.5 deals with fluids in motion. There are two assumptions we have. One is laminar flow as opposed to chaotic flow. The other is that fluids are incompressible. So we think about an ideal fluid as being one with laminar flow. I've got a neat video from the YouTube channel Smarter Every Day about that. That guy really was excited about laminar flow. It is pretty cool. These are the two equations that go along with that. We'll have to talk about those a little bit more. This is a continuity equation. Area times velocity is equal to area times velocity in a different part of a closed pipe or closed tube. But basically that says is the volume flow rate is constant. So if I end up with area is square meters, so if you think about a pipe, it might be pi r squared, we would think about to get that area, times the velocity in meters per second, we get a cubic meters per second is the flow rate. Well, that flow rate has to be the same everywhere in a closed system of a pipe. So if you have a smaller cross-sectional area, the fluid would have to be flowing faster to have the same number of cubic meters per second or cubic meters per unit of time. That also you could think of is a flow rate in terms of things like gallons per minute or quarts per minute or liters per second or something like that. But the traditional units here would be cubic meters per second. This scary long equation, which is F6, if you can see it, so F5, 4, F3, F2, F1, and these are the 6 fluid equations, is Bernoulli's equation. And if you look here, this looks an awful lot like the equation for gravitational potential energy, mgh. Well, this is pressure at one location in a pipe, plus rho gh, density g, height of location at location 1. This, 1/2 rho v squared, looks a lot like 1/2 mv squared, which is kinetic energy. So this really is kind of an energy equation, which is pretty neat. And then at a second location in the pipe, you'd have those same things again, those same factors. Oftentimes you might have to figure out the velocity using this continuity equation and then plug it in here. This looks really, really messy, but oftentimes you know almost everything in it. For example, this rho term is density. Whatever it is would be the same for all four of these terms. Oftentimes, the lower spot of the pipe, we would think of H1 as being 0, so that whole term would go away. And again, these are things we could work out. Usually what you're trying to do is figure out the pressure at one spot of a pipe if you know the pressure at another spot of the pipe. So the only thing that's a little tricky is with this, again, you might have to use pi r squared to get the area. So that's some of the general background that we might not get to in class. I'm going to do a couple examples next. Welcome back. I want to go through a couple example problems. Actually, we'll go through several example problems because there's a lot of different types from chapter 13. So I'm going to try to do 2 here in the next part of the Ed puzzle. So this is actually problem 9 out of your textbook, similar to other ones you'll have assigned. This is problem 34 out of your textbook, similar to other ones you'll have assigned as well. So over here, what we've got is a tall cylinder, so think of it like a graduate cylinder, contains 25 centimeters of water. Oil is then poured on top until there's a total depth of 40 centimeters. You want to find A, the gauge pressure at the bottom of the cylinder, and B, the absolute pressure at the bottom of the cylinder. Now to know this, we're going to have to use some of these formulas. This one in particular is the one that's going to be important. So this is the absolute pressure, atmospheric pressure, and then this would be the gauge pressure. Well, because we've got 2 different fluids here at different depths, we're going to have to think about finding the gauge pressure, which is basically caused by those particular fluids, in pieces. Now, in order to do this, we need to know the densities of those materials. So, density of water, and this is something given in your textbook, is 1,000 kilograms per cubic meter, and the density for oil, there's many different types of oil, so I think this is just an average, 900 kilograms per cubic meter. So hopefully it makes sense that the oil floats on the water because the oil is less dense than the water. Okay, in this particular case then, so what I would end up doing, I'm going to move this off to the side momentarily. I'm going to say the pressure of the water is equal to rho, which is the density. Actually, I'm going to call that D for depth. It's a little inconsistent with what I have over there. Is 1,000 kilograms per cubic meter plus 9.8 newtons per kilogram. Nope, not plus, times. I'm an idiot. And then multiplied by a depth of 0.25 meters. And when we do that, we get that the pressure caused by the water is equal to 2,450 pascals. So we go back and do the same thing for oil. 900 kilograms per cubic meter multiplied by 9.8 newtons per kilogram multiplied by a depth of not 0.4 meters, but the total depth is 0.4 meters, so 0.4 minus 0.25 would be 0.15 meters. That's going to be less, obviously. And that's going to be around 1,300. Let me check here, make sure I did my math right. It looks scribbly. 0.15 times 900 times 9.8, 1,323. So the absolute pressure would be, the gauge pressure would be both of those added together. So I can do math. $3,773 pascals. So that's what the gauge pressure would be. To find the absolute pressure, we're going to go back to this version. That's P absolute. P0 is atmospheric pressure plus the gauge pressure here. The gauge is all those rho g depths multiplied by together. So your textbook uses atmospheric pressure as 101,300 pascals, or 1.01 times 10 to the fifth pascal, or 1.013 times 10 to the fifth pascals. The AP says it's okay to use 100,000 because it's different in different parts of the world, and 101,300 is a little too specific. It's at sea level at a certain temperature. I'll use what the book uses, though, just to be consistent. So that's going to be 101,300 plus 3773, which is our gauge pressure. So that's basically going to end up being about 104,000 or 105,100 pascals when I round. Like that. So this absolute pressure would be what we would use if we needed it for other calculations, but this oftentimes is useful when thinking about a net force between two objects. I'm going to erase this over here and do the second problem. I might not need to. Just move this over. So this case says you have a 6,000 liter swimming pool. Water drains out of a 2.5 centimeter diameter hose, so that's 2.5 centimeters all the way across, at 2.1 meters per second through a pump. If it wasn't through a pump, it wouldn't maintain a constant speed. As the level of the pool got lower, the rate at which it would drain would get lower because the pressure would get less at the bottom. There's something else we could figure out about that. So the question is how much time is it going to take the pool to drain? It said how long is the pool going to drain? So that's problem 34 out of the back of our chapter. So the key thing here is to figure out what's the volume, and if we know the rate at which it's draining in the cross-sectional area of the hole, we can figure out the flow rate, and then we can use a quantity equals rate times time to figure out the time it's going to take to drain. So the first thing I've got to do is do 6,000 liters, and I know that a liter is 1 cubic decimeter or 1,000 cubic centimeters or 1,000 milliliters. You may or may not be aware of that, but I'm going to do a conversion here. 0.001 cubic meter is over 1 liter. So that is the conversion for that. So that means we end up having 6 cubic meters as a pool. Sounds small, but humans as a volume are somewhere normally around 0.1 cubic meters. It seems like we should be more if you think about it, but we're not. Okay, so we've got something like that. Q, a lot of times in your chapter, is known as the volume flow rate. In cubic meters, that would be this times this. Okay. So I need to figure that out, and to do that, I need to figure out this speed times the cross-sectional area. So the area of a circle is pi r squared. So in this case, it's pi. This was 2.5 centimeters, so the radius would be half of that, 1.25 centimeters. That's 0.0125 meters squared. So the area is equal to 4.9 times 10 to the negative 4th cubic square meters, pardon me, not cubic meters. So when I do that and I multiply it by the speed, .1 meters per second. I hope that's visible. Just barely is visible. That gives me my volume flow rate, which in this case is 1.03 times 10 to the negative third meters cubed per second. Hope that's still in there. Yep, just barely in there. So in this particular case, then now I know my flow rate and I know my volume. So I could say that in this particular case, time equal to volume divided by rate. got 6 cubic meters. We're leaving at this amount of cubic meters per second. Cubic meters divided by cubic meters cancels out. Second is in the denominator. That makes it in the numerator. So my answers would be in seconds. I should end up with quite a few, 6 divided by a small number. And in fact, that gives me about 5,820 seconds. And that's a little less than 2 hours. That's about 1.6 hours. Not a little less. That's a decent chunk less than 2 hours. So that's how we go through that type of problem.